Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 3.2 on linear functions. Well, that's a nice word, linear. And the essential question is, how can you determine whether a function is linear or nonlinear? Well, first of all, we have to know what linear means. So let's take a look at some definitions here first. And the first is a linear equation in two variables. That's kind of that's a phrase, I guess we're going to call it a phrase that we're going to run across a lot. Linear equation in two variables, x and y, is an equation that can be written in the form y equals m times x plus b. Okay, make sure you're getting all this vocabulary in your notes. Next, a linear function. Well, this is very similar to a linear equation, but we're just going to say that a linear function has a graph that is a non-vertical line due to a constant rate of change. Okay, so make sure you get all this in there because this idea of rate of change is really important in what makes a function linear. And then finally, a nonlinear function. It does not have a constant rate of change, so it's not going to be a straight line. Linear functions are straight line, nonlinears are not straight lines. And it has to do with this constant rate of change. So get these in your notes. Pause the video if you need to catch up. Otherwise, I'm moving on right here. So pause it, and I'll catch you later. Hey, welcome back. So first of all, we just have to say, we have these two graphs here. Are these linear or nonlinear? Well, when we say linear, we're talking about a straight line. A straight line. So obviously A is nonlinear and B is linear. Okay. This idea of well, I don't want to say this in absolute terms, but essentially linear graphs of linear functions. Well, the equations, they have a slope, if you're familiar with slope, because that's the rate of change we're talking about. And we'll get more into that in a little bit. That's not to say that these don't have slope, but these slopes are constantly changing is the problem, and that's what calculus is. Let's move back over to this side for algebra. It's a constant rate of change, so we get a straight line. This one's linear. And you can tell by looking at the graph. Tables. Here's what we need to do. We need to compare the rate of change. When we say rate of change, we're talking about how y changes compared to x. It's a ratio. Again, it goes back to this idea of slope. And if you haven't had that yet, this is kind of a review. So let's look at A. What's happening here with A? X is increasing by 3. 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. The y values, how are they changing? 36 to 30 would be a minus 6. 30 to 24 is a minus 6. And 24 to 18 minus 6. So we have a negative 6 change for every positive 3 change in the x values. So this has a constant rate of change of 2. Or again, we call this slope when we refer to the line. We refer to the angle of the line, or how the line is positioned on the coordinate plane. Let's take a look at the second example here. 1 to 3 is a plus 2. Okay, so it looks like the x values here, the domain values, are increasing by 2. And then we have 2 to 9 is plus 7, and then 9 to 20 is plus 11, and then 20 to 35 is plus 15. So this is not a constant rate of change. When I say constant, I mean it's the same. So here, 6 to 3, or negative 6 to 3, negative 6 to 3, negative 6 to 3. It's a constant rate of change. Here is 7 to 2, 11 to 2, 15 to 2. This is not constant, so this is going to be a nonlinear function. I'm not going to get that nice straight line. And this one is linear. Okay. Now this is kind of messy. Let me kind of separate these here for us. And the question is, which of these represents linear functions? And we're looking at equations here. There we go. And remember, one of the definitions for linear equations is that it can be written in the form y times m, y equals m times x plus b. So can we rule any of these out right away? Well, I'm going to start over here. X squared. We can rule out x squared because there's no square. This x is not squared. So x squared, no, that's not going to be linear. As a matter of fact, later on in the year, we'll deal with those and we'll call those quadratics. But for right now, no. This one, y equals 2 divided by x. Well, is there a way I can write this as x times something, like multiplying by the inverse or something like that? And I really can't. I really can't think of this as 2 divided by x. It's not x times something. This is really a 2 times the inverse of x. So this is not a linear function here. This one here, x is as the exponent, so this is not going to be linear. And this one here, we're taking the square root of x, so this is not going to be linear. Again, x is just multiplied by something and added to or subtracted from, so that's not. Okay, let's take a look at this one over here. Y equals 6 times the quantity x minus 1. Well, if I use distributive property, boom. And I'm going to write it like this. I'm going to write plus negative 6, so we can kind of have this idea of plus b, right? So plus negative 6 or minus 6, same thing. So this has, I can write this equation like this. So this is a linear function. What about this one? Y equals 3.8. Can I write this like this? And I can, and it looks like this. Y equals 0x plus 3.8. 3.8 is just a plain number. There's no variables by it or anything. So that's actually the b value out here. And 0x, well, it has this form, doesn't it? But why don't I have it up here? Well, because we simplify. What is 0 times x? 0 times x is 0. And what's 0 plus 3.8? 3.8. So y equals 3.8. So even though we don't see the x, it's there. It's just being multiplied by 0. So this one's linear, and this one's linear. The others are not for the explanations I gave. Squared, dividing, exponent, square root. No, none of those. Okay, let's take a look what is next. The linear function y equals 15.95 times x represents the cost y in dollars of x tickets for a museum. Okay, kind of makes sense, right? 15.95 per ticket times the number of tickets equals that total cost. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Is the domain discrete or continuous? Well, x is the number of tickets. X is the number of tickets. So you have to ask yourself, since domain is number of tickets, and discrete means separate. Discrete means separate, and continuous is like all together. You kind of have to ask yourself, can I buy like fractions of a ticket? Can I buy like 1.001 ticket, 1.5 tickets, 1.95 tickets? And the answer is no. Tickets, you buy 1, 2, 3, 4. You don't buy partial tickets. So in this case, the domain is discrete. And it says graph the function using its domain. Okay, so if I was to graph this function using its domain, I could put a table together like so. I'm just going to do a rough sketch here, and I'll have 0 tickets, 1, 2, 3, 4. That's the maximum. Okay, so the domain here, of course, is 0 to 4, because that's the most I can buy. And then if I multiply by 15.95, every ticket is $15.95. I would have $0, $15.95, $31.90, $47.85, and $63.80. And then I would plot these ordered pairs as my graph. And I don't want to sketch that graph right now because it would be a little messy. I would prefer to have a graph all laid out here. But these are the ordered pairs I would graph. And I would not connect them with a line because, again, these are discrete values, discrete ordered pairs. Last example here, cereal bar contains 130 calories. The number of calories C consumed is a function of the number of B bars eaten. Does this situation represent a linear function? Well, sure, because the rate of change is constant. 1 bar, 130 calories. 2 bars, 260 calories. 3 bars, 390 calories. Oops, 2, 260, and 3, 390. So this is linear. I have a constant rate of change. The domain of the function, is it discrete or continuous? Well, in this case, you can eat half a bar. You can eat just a little nibble of the bar, and maybe it's 1/1000th of the bar. But in this case, you can. So this one is continuous. And for this one here, I would graph these ordered pairs, and I would draw a line through it. Draw a line through it on the graph. And you would just use an XY graph like this and draw that line after plotting these points. Again, I'm not going to do it because it's going to be wildly inaccurate trying to do it on this thing without a template. Okay, but the idea here is this one is continuous because you can eat fractions of the cereal bar. Okay, that's the big idea I want you to think about. Discrete and continuous. This one's continuous. Tickets are discrete. Okay, that's it. Another little puzzle for you. There's still a lot to do in this lesson. So the in-class tomorrow or whenever we meet again is going to be a little more hectic, but I'll see you in class. Thanks a lot. Have a great rest of your day.